All right, so while we were in class, we covered sections 8.1 to 8.4. We talked about the types of bonds and we talked about ionic, covalent, and metallic bonding. We looked at ionic bond strength with lattice energy. We briefly looked at Lewis dot diagrams and had an introduction to Lewis structures, single, double, and triple bonds. And we looked at the relative strength and length of single, double, and triple bonds. However, we're going to move on now to sections 8.5 to 8.7, and we're going to look at exactly how to draw Lewis structures, and I'm going to throw in a few types of structures that are not covered in the book, but you will see on the AP exam. All right, so let's first outline the rules. Now, all of these steps are in your notes. They're also on your Lewis structure worksheet, and there's a couple supplements on the website that you can look at. But you need to have these rules in front of you in order to actually understand and complete a Lewis structure. First one, sum up the valence electrons. And the group number is the number of valence electrons. If you have a negative charge, you're adding electrons. If you have a positive charge, you're taking away electrons. Next, choose a central atom. The least electronegative. You know the trend for electronegativity. It's up and to the right. So things that are down here are the least electronegative. Hydrogen is never the central atom. Never ever. Then you're going to arrange all the other atoms around the central atom and connect with a single bond. Based on the remaining electrons that you have not used, you're going to complete the octet for the exterior or the outside atoms. Remember, hydrogen can only have 2 electrons or 1 bond. Put any leftover electrons on the central atom. If needed, you can often skip steps 4 and step 5. And if the central atom does not have an octet, you're going to borrow a lone pair from a neighboring atom to make a double, and sometimes you'll have to do a triple bond. So keep these rules handy, and we're going to go through some examples. Let's look at PCl3, our first example. Step 1, we're going to sum up the valence electrons. Phosphorus is in group 5. Chlorine is in group 7. There's 3 chlorines, so 3 times 7. So that's a grand total of 26 electrons. Think of this as the electrons in the bank. You can't spend any more than this. You can only use 26 electrons. All right, step 2, we're going to choose a central atom. Phosphorus is the least electronegative, and we're going to arrange everything else around it with a single bond. Step 3, we're going to distribute the remaining electrons to the exterior atoms. Well, I've used 2, 4, 6. I've got 26, so I've used 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and that's step 3. I've distributed the remaining electrons to the exterior atoms to give them an octet. Each of the exterior atoms has an octet. Moving on, step 4 says if you have any leftover electrons, which we do, we had 2, we're going to put them on the central atom. Step 5, if our central atom does not have an octet, we're going to use multiple bonds. Well, look, our central atom has 8 electrons around it. So every time you see a single bond, that means that both of the atoms involved own those electrons. So phosphorus technically owns both of the electrons here. Chlorine owns both of the electrons in there. So you can think of it like that when you're counting. That Lewis structure is done. Next one, HCN. Step 1, sum up your valence electrons. Hydrogen is a +1. Carbon, group 4. Nitrogen, group 5. So that gives us 10 electrons in the bank. Step 2, we're going to choose our central atom, which is the least electronegative. Remember, hydrogen never goes in the center. carbon is less electronegative than nitrogen, so we're going to attach the remaining atoms with a single bond. That's step 2. Step 3, you can distribute the remaining electrons to the exterior atoms. Well, we've used 2, 4. Now, you can't put any more on hydrogen. Hydrogen can only have 2 electrons. Why? Because its outermost electrons are in the first shell, which can only accommodate 2 electrons. So we've used 2, 4, 6, 8, 10. We're out of electrons. All right, so that means we're not using step 4. Step 4 says if you have any extra electrons, put it on the central atom. However, in this case, we're out. Step 5 says, look at the central atom. Does it have an octet? Right now, carbon has 4 electrons. That's not 8. So what we're going to have to do is borrow electrons from a neighboring atom. Well, hydrogen does not have any more electrons to borrow. So carbon looks to nitrogen and he says, hey neighbor, can I borrow a pair of electrons? Nitrogen says, sure, but we're going to have to share them. So we're going to get rid of these, and now they're going to share that pair. Now carbon's got 6 electrons around it. Carbon's not happy yet. So carbon's going to need another pair of electrons. Can't borrow from hydrogen. He looks over at nitrogen and says, hey neighbor, can I borrow some electrons? He says, I guess we can share them. So now they're sharing them. So each of our atoms is happy now. Carbon's got 8, nitrogen's got 8 around it, and hydrogen's only got 2 electrons, but that's what hydrogen likes. Next, we're going to look at the Lewis structure for NO3. This is the nitrate ion. So we're going to sum up our valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6, but there's 3 of them. And then that negative charge, that means you add an electron. So we've got 18 plus 6 is 24 electrons in the bank. Step 2, we're going to choose a central atom. Nitrogen is the least electronegative. We're going to arrange all the other atoms around it with a single bond. Step 3, we're going to distribute the remaining electrons to the exterior atoms. We've used 2, 4, 6. So now let's add them. 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm out of electrons. Step 4 says if you have any extra, put it on the central, but we don't have any extra. Step 5 says check your central atom. Does it have an octet? Nitrogen only's got 6 electrons, so nitrogen is not happy. What are we going to do? We're going to have to borrow electrons from a neighbor. Now, it doesn't matter which one of these I choose. I could borrow electrons from any of these oxygens, but let's just go with the right one. Nitrogen says, hey, oxygen, on the right, can I borrow some electrons? Oxygen says, well, how about we share them? Nitrogen says, fine. Nitrogen's got 8. All of the oxygen atoms have 8 electrons. Everybody's happy. So these are your basic Lewis structures. From here, you should be able to complete the first Lewis structure worksheet. So make sure you go through Lewis structure worksheet number 1, complete all of those problems. Some exceptions to the octet rule. We can have atoms that are electron deficient, which means less than 8. So you must know all of these that are exceptions to the octet rule. Hydrogen only likes 1 bond. That means 2 electrons can be accommodated in that outer 1s orbital. See, hydrogen only likes 1 bond. Boron likes 3 bonds. This one, they like to throw out on the AP test every once in a while. Don't get fooled and get to this point of a Lewis structure and put a double bond for boron. That would be wrong. Boron only likes 3 bonds, 6 electrons in its outer energy level. Beryllium is a weird one. It only likes 2 bonds or 4 electrons in its outer energy level. So what do you have to remember? Hydrogen, boron, lithium. Hydrogen likes 1 bond, boron likes 3, beryllium likes 2. Very rarely will you see beryllium on the AP test. They used to put it on there. They haven't put it on in years. Next, we're going to talk about atoms that can exceed the octet rule, meaning they can accommodate more than 8 electrons. So central atoms that can accommodate more than 8, those are anything in the third period or below on the periodic table, third period or heavier. So look at those elements. Listen, the third period elements have their outermost electrons in the third energy level. The third energy level, or third principal energy level, has sp-d orbitals, 2 in the s, 6 in the p, and 10 in the d. That's 18. So all of those elements can, not that they will, they can accommodate more than an octet if needed. They have that empty d orbitals to accommodate those extra electrons. Very important. You need to know that. So some examples are SF6, PCl5. SF6 has 2, 4, 6, 8, 10, 12 electrons around its central atom. PCl5 has 10. Sometimes you'll see lone pairs on the central atom. So let's just go through that one. If you had XeF4, if we add up our valence electrons, so xenon is 8, there's 4 fluorines, each one is 7. So that gives us 36 total electrons. Xenon in the center, everything else around with a single bond. All right, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's step 3. Step 4 says if you have any extra, put them on the central atom. So I've used 32. We're going to do 34 and 36. What I don't want you to do is to arrange them like this. Don't say 1, 2, 3, 4. You keep the lone pairs together in this instance. It just is what it is there. Keep them together. All right, we're going to talk about simple hydrocarbons. You will need to know how to draw a Lewis structure for hydrocarbons and different functional groups. So we will talk about functional groups later. However, let's learn to draw simple hydrocarbons. Now, you did this in honors chemistry. Remember, we had methane, ethane, right? We had CH4, and then I had you drawing, here's ethane, CC, and then propane. This is just a refresher from last year. All right, and then I showed you how to draw bond line structures. There's no bond line for methane. All right, so we did all that last year. We're going to expand upon that here. So we're going to draw a Lewis structure for simple hydrocarbons. If you want to do this systematically, sum up your valence electrons. Form a carbon conga line. Attach all the carbons in a row. Attach the other atoms. Attach anything other than hydrogen to the carbon chain. At this point, it doesn't matter which carbon you put it on. All right. Then we attach the hydrogens. Remember, carbon likes 4 bonds, so oxygen likes 2 and nitrogen likes 3. So you can fill in hydrogens to accommodate all the number of bonds that each one of these likes if we need to. We fill in the remaining electrons and then we use multiple bonds if necessary. Let's look at C2H6. Let's sum up the valence electrons. We have 2 carbons, so 2 times 4 plus 6 times 1. So that equals 14 electrons. All right, we're going to form a carbon conga line. Put all your carbons together. Next, we're going to attach anything other than hydrogen. Well, we don't have any of those. Next, we're going to attach our hydrogens symmetrically. And we don't have any other electrons. We've used 2, 4, 6, 8, 10, 12, 14. So we don't need any multiple bonds here. Every atom is happy. All right, let's do C2H4. We have 2 carbons, 2 times 4 plus 4 times 1. That's 12 electrons. Let's make a carbon conga line. We don't have any atoms other than hydrogen, so let's arrange them symmetrically. All right, we've used 2, 4, 6, 8, 10. Now we have 12. I can put a pair of electrons on any of these carbon atoms. It doesn't matter. We could treat this as the central and say put the pair on the exterior atom. That doesn't matter. All right, so now let's check. Is every atom happy? All the hydrogens are happy. Our carbon on the right is happy. It's got 2, 4, 6, 8, but our carbon on the left is not happy. I think you know what we have to do here. We have to get rid of that lone pair and make a double bond. Let's look at the next one. C3H7OH. So there's step 1, sum of your valence electrons. There's 3 carbons. There's 7 hydrogens. There's an oxygen. And then we have 1 more hydrogen. 12 plus 7 plus 6 plus 1. So that's 26 electrons. All right, we're going to make a carbon conga line, CCC, and we're going to attach elements other than hydrogen to our carbon chain. Now, it doesn't matter which carbon I put it on. You can put it on the middle one, the left one, or the right one. At this point, who cares? Next, we're going to attach our hydrogen atoms, making sure that each atom has the number of bonds that it likes. You need to know this. Carbon likes 4 bonds. Nitrogen likes 3 bonds. Oxygen likes 2. Halogens, X, like 1 bond. So oxygen likes 2 bonds, so it gets 1 hydrogen. Each of these carbons. Right, so now each of those carbons have 2, and our final carbon here can get 3 to satisfy the bonding patterns. I have a total of 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and we fill in our lone pair. The only place that we can put any more electrons is on the oxygen, and our Lewis structure is done. All right, what I want you to do is stop the video and try these in your notes. You should have the notes in front of you, and it's exercise 6. When you come back, I'll give you the answers. All right, hopefully you're able to give these a try. Let's look at the first one. We have CH4, that's 4 plus 4 times 1. That gives us 8 electrons. Carbon goes in the center. Hydrogens on the exterior. And our Lewis structure is done. For B, we have 4 plus 2 plus 6. That gives us 12 electrons. Carbon goes in the center. Remember, hydrogen never goes in the middle. We've used 2, 4, 6, 8, 10, 12. We're out of electrons. We don't have any more electrons to put on the central atom. So step 5 says if your central atom is not happy, which carbon's not, it has 6 electrons, we're going to need to use multiple bonds. Carbon can only borrow electrons from the oxygen, so we're going to get rid of that lone pair and make a double bond. BRF5, we have 7 plus 5 times 7, so that equals 42 electrons. Bromine is less electronegative, and hopefully you're seeing the pattern here. When you only have one of a particular atom, that's the one that goes in the center. I arrange everything around the central atom connecting with a single bond. That's step 2. Step 3 is we're going to distribute the remaining electrons to the exterior atoms. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. At step 3, we're done. We've used 40 electrons. Step 4 says if you have any extra electrons, you put them on the central atom. Step 5, we're going to skip because all of our atoms have an octet. Bromine has to have more than an octet. Why can bromine exceed the octet rule? Because it has d orbitals available for bonding. Bromine is below the 3rd period. Next, let's look at the nitrite ion. 5 plus 2 times 6, and that negative charge means we add an electron. That's 12 plus 6, that's 18 electrons. Nitrogen goes in the center. We're going to attach our oxygens with a single bond. Step 3 says we're going to distribute the remaining electrons to the exterior atom. So I've used 2, 4, 6, 8, 10, 12, 14, 16. I've got 2 more. We're putting them on the central. That's 18 amount of electrons. Everybody's happy except for nitrogen, which has 6. So it doesn't matter which of these oxygens you borrow electrons from, but we make a double bond and we get rid of that lone pair. Next, C2H2, simple hydrocarbon. 2 times 4 plus 2 equals 10 electrons. Carbon conga line. We don't have anything other than hydrogen, so we're going to put our hydrogens on symmetrically. And we've used 2, 4, 6, 8, 10. Now, everybody's happy except for our carbon on the left. So he's going to have to borrow a lone pair. We'll make a double bond, but carbon's still not happy. We're going to have to borrow another pair to make a triple bond. For our next molecule, we've got 4 times 4 plus, there's a total of 10 hydrogens, and there's 1 oxygen, so that's 6. So we've got a grand total of 26, 32 electrons in the bank. We're going to make a carbon conga line. We attached atoms other than hydrogen, so let's put our oxygen on there. Now we're going to add our hydrogens to make each of the atoms happy. Oxygen likes 2 bonds, so we're going to give it that hydrogen. Carbon likes 4, so let's make each of our carbons happy. There we go. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. I've used 28 electrons. I've got 32, so I'm going to have to put some extra electrons on the oxygen. And our Lewis structure is done. All right, moving along, Lewis structures of oxyacids. Now, this is not in the book, but you do need to know this for the AP exam. An oxyacid, you know the oxyacids. They take the form HXO. It's an acid that has an oxygen, oxyacid or oxoacids. Here are some tricks. Never ever bond hydrogen to the central atom when you're doing this. The hydrogen always goes on the oxygen. Attach it with a single bond. And it's often helpful to draw the oxyanion first and then add the hydrogens. Let me show you some examples here. We have acetic acid. Notice the hydrogen. This is the acidic hydrogen, or the acidic proton. It's always attached to the oxygen. These are not acidic. All right, we have another example, sulfuric acid. Notice how we have the hydrogens on the oxygens. Now this structure can be optimized, but we'll talk about that later. Okay, so based on what you know, draw the Lewis structures for the following acids. Okay, nitrous acid. Pause the video, give it a try. When you come back, we'll give you the answer. All right, let's take a look. We have 1 plus 5 plus 2 times 6. So that gives us 12 plus 6 is 18 electrons. Nitrogen is less electronegative than oxygen. And this is an oxyacid, so we're going to put the hydrogen on one of the oxygens. It doesn't matter which one we put it All right, next we're going to distribute our remaining electrons to the exterior atoms. I've used 2, 4, 6, 8, 10, 12, 14, 16, and I'm going to have to put 2 on the central. That's 18. Nitrogen's not happy. So we could choose to make a double bond here or here. Now let's think about our bonding patterns. I recently told you that oxygen likes 2 bonds. So look, this oxygen on the right already has 2. Why wouldn't we give the oxygen on the left the double bond? Right, so now everybody's happy. Lewis structure is finished. Let's look at phosphoric acid, H3PO4. So we've got 3 times 1 plus 5 plus 4 times 6 is 24. So that gives us 32 electrons to use. Phosphorus goes in the center. Attach your hydrogens to the oxygens. There's only 3 of them, so we're out. So now let's take a look. We've used 2, 4, 6, 8, 10, 12, 14 electrons, 16, 18, 20, 22, 24, 26, 28, 30, 32. Everybody's happy. All right, now that we know how to draw Lewis structures, we need to learn about formal charges so that we can then optimize our Lewis structures. You cannot optimize a Lewis structure until you know how to calculate formal charges. Formal charges are simply an electron accounting method for atoms. It tells us how many electrons or how the electrons are distributed within the molecule. Formal charges also show us reactive sites of a molecule as well, but you don't need to know that for right now. So formal charge can be calculated using several different equations. I'm going to show you the simplest one. It's the number of valence electrons minus the number of electrons that particular atom owns. And the sum of the formal charges equals the charge of the molecule. This is how you're going to check your work, by summing up the formal charges. And if they don't all add up to the total charge of the particle, then you've done something wrong. Let's calculate all the formal charges for the nitrate ion. Well, we know that nitrate looks like this. Okay, let's start with this oxygen. That's maybe the hardest one. Remember, the formal charge equals the group number, or the number of valence electrons, minus the number of electrons owned. So the formal charge for this one is going to be the group number of oxygen, which is 6, minus the number of electrons owned. Well, oxygen, let's see, there are 4 electrons in that double bond. We're going to give 2 of them to oxygen. We're going to give 2 of them to nitrogen. So now look at this oxygen. It owns 2, 4, 6. So 6 minus 6 equals 0. Let's take a look at this oxygen. The formal charge equals group 6 minus the number of electrons owned. Well, in that bond right here, in that single bond, we're going to give 1 to oxygen, 1 to nitrogen. Let's look at our oxygen. It owns 7, so that has a -1 formal charge. So oxygen is group 6. It has 6 valence electrons. When it has 6 valence electrons, it's neutral. When it has an additional electron, it gets a negative charge. And when it has less than 6, like 5, it would have a positive formal charge. Let's look at our next one. The formal charge equals group 6 minus, well, in this single bond, we're going to give 1 to oxygen, 1 to nitrogen. So 6 minus 7 equals a -1. So we've got a -1, a -1, a 0 so far. And finally, let's do our nitrogen. the formal charge equals nitrogen's group 5 minus, how many does it own? It owns 4, so that's a plus 1. Now let's add up all of our formal charges. Plus 1 minus 1 minus 1 equals, oh, look at that, total charge in the particle. All right, I'd like you to pause the video and give these a shot. When you come back, I'll give you the answers. You're going to be calculating the formal charges on each atom. All right, hopefully you were able to give these a try. And here are the answers. This oxygen is a -1. This oxygen was a +1. That was a 0. Each of the hydrogens were 0. The nitrogen was a +1. Hydrogen 0, 0, carbon 0, nitrogen 0, hydrogen 0, 0, 0, 0, 0, and that's a -1. All right, so now we need to optimize our Lewis structures, and we want to be able to choose the best structure. So we're going to sort of kill two birds with one stone, choosing the best structure and optimizing it. All right, number one, and we follow these rules in order. We want the formal charges to be closest to 0. So if I have two options, if I have resonance structures where I can put a double bond in more than one place, or you're just comparing two different Lewis structures to the same molecule, we first want to assign formal charges. And when we do that, we see our oxygen is 0, sulfur is +1, -1, and here everything is 0 in molecule 2. So this number 2 is the best structure because it has formal charges closest to 0. Now here's a trick. When you have an element that is a third period or below that can accommodate more than an octet, and you see a +1 and a -1 formal charge next to each other, you can cancel them out by, look at this blue arrow, you make a double bond. All right, this optimizes the Lewis structure. So whenever you have a +1 and a -1, the double bond can be added to minimize the formal charge. This is only possible for third period and below on the table. The octet rule is exceeded here. The next rule is if you have a choice of multiple Lewis structures putting a negative formal charge on a different atom, you want to put it on the more electronegative atom. You want to put the negative charge on the more electronegative atom. Extremely important. They have this on the AP test almost every year. All right, so let's take a look. Our worst structure, if we're ranking these, number 3 is the worst because it has formal charges furthest away from 0. They're too high. Charge separation costs energy. This is a high energy molecule. All right, now, between our first two, 1 and 2, we can put a negative charge on sulfur or a negative charge on nitrogen. Well, sulfur has an electronegativity value of 2.5. Nitrogen has an electronegativity value of 3. So nitrogen is more electronegative. With the negative formal charge on the nitrogen, this molecule is more stable. So 2 is the best. Since the formal charges are minimized and the negative charge is on the more electronegative atom. 3 is the worst because the formal charges have the greatest magnitude. All right, I'd like you to give this one a shot. Pause the video, try to rank these, determine which is the best Lewis structure. All right, so let's take a look. We assign our formal charges first. This is a -2, 0, +1, we have a -1, 0, 0, and we have a 0, 0, and a -1. So this is going to be our worst. Now we have a negative charge on nitrogen, we have a negative charge on oxygen. 3.0, 3.5, this is more electronegative. right? So when we have a choice of putting the negative formal charge on different atoms, the best Lewis structure will have the negative charge on the more electronegative atoms. So this is your best. This guy's okay. All right, our last section, resonance. Now, I saved this for later because I feel it just fit better after we learned about some of the other stuff first. However, resonance structure simply occurs, well, let's keep it simple. When you can put a double bond in more than one place. Okay, that's how you can draw more than one resonance structure. Now, resonance simply means that resonance occurs because free and pi electrons meaning electrons in a double bond, those electrons can be delocalized or spread out over multiple atoms to lower the energy of the molecule. So we'll take a look at in a few other examples. But let me show you the carbonate ion first. All right, this has several correct Lewis structures. Now, you would have gotten to a point drawing your Lewis structure for carbonate where you were here. And you would have to choose which oxygen should you make a double bond to, because carbon's not happy, right? Carbon had 6 electrons. It needs an octet. So it's going to need a double bond with one of these oxygens. You could have drawn that double bond with any of them. So the fact that you could have drawn 3 different correct Lewis structures means that these are resonance structures. These happen to be 3 equivalent resonance structures. In our previous section, we were just looking at resonance structures that were not equivalent because we ranked them. You just didn't know they were resonance structures. So these happen to be 3 equivalent resonance structures, and you could go through the rules. The charges are the same, and the negative charges are on the same types of atoms. All right, so these are all identical. Notice we have a double bond here, here, or here. We put double-headed arrows for resonance. Don't confuse this with equilibrium arrows. That's for equilibrium. The double-headed arrow is for resonance. All right, this is important. This shows up on the AP exam almost every year. Understanding the resonance hybrid. So you don't necessarily have to draw the resonance hybrid. However, you have to understand that the true structure doesn't really, or the individual resonance structures don't really exist. The true structure is really an average of all 3 resonance structures, and that average is called a resonance hybrid. So let me give you a much simpler example. Here's an allyl cation. You can draw 2 resonance structures for this. And neither of them really exist. The hybrid is an average, and what we do is we draw a little dotted line connecting all the atoms where we see that double bond switching places with. All right, instead of full charges, we have partial charges. That would be a partial positive and a partial positive. So what the hybrid does is it shows the average of our resonance structures, and it more accurately portrays where the electrons are. Okay, so important. All of these carbon-oxygen bonds in our carbonate are equal. What? They're equal? Well, there were 3 resonance structures, and I had 2. Look, in each one, you had 2 single bonds and 1 double bond. But studies have shown that the bonds are all equal. Well, why? Because of the resonance hybrid is really an average of all 3 of these, and in reality, the electrons are shuttling around and spread or delocalized. So what we see is instead of having a -1 charge on two of these, right? So that's a -2 spread over 3 atoms. -2 over 3. So these are all equal in length. Now single bonds are the longest, then double bonds, then triple bonds. Would we expect these bonds to be greater than a single bond or shorter than a single bond length? Well, if they're somewhere in between a single and a double, we'd expect the bond length to be somewhere right between a single and a double bond length. All three of these should be a little bit shorter than a single, but a little bit longer than a double. All right, so I'd like you to draw 3 possible resonance structures for the nitrate ion. Pause the video, and when you come back, I'll give you the answer. Right, hopefully you're able to determine all 3 resonance structures for nitrate. Here's one. Resonance structures, you draw your double-headed arrow, you put it all in brackets. Now we could put our double bond here. We could also put our double bond down there. Okay, so like I said, resonance occurs because the delocalization of electrons or the movement or spreading out of charge stabilizes the molecule. So the electrons that are able to move stabilize the molecule, and this is called delocalization or resonance stabilization. Benzene, for example, has 2 resonance structures. I just want to show you molecules in a ring. Let me show you with arrows. These are curved arrows which show the movement of electrons. You don't need to be able to draw these, but I'm just showing you how the electrons are moving. So we see that we get 2 resonance structures. Now these are bond line representations. You don't need to know how to do that. But this is often how you see benzene, or we can also draw benzene as a hexagon with a circle in it. Because all of the electrons are delocalized, they're constantly moving. So what would the resonance hybrid look like for this? Kind of like that.